Alright, so I kind of disappeared on you guys last week. It was just Barrett was not doing well, and so I didn't have the time or energy to Skype you or make videos or anything like that. He's doing much better now, much more stable, so hopefully this week, well, in the 2.5 days, I'll be talking to you more. I sent you guys the answers for these problems, but I have no idea how well you got it. So I'm going to go over them and give you some, just talk about them and then give you some more problems to do like them. Because I know last time we talked, you weren't feeling it. So the whole thing on all of these is you're obviously going to be using derivatives, and the whole thing is just identifying like what the derivative of what function you have, what your variables represent, and if you do the derivative, what that derivative represents. Because that'll answer all the questions that you need to answer. So like 14. It says it gives you equations for free fall near the surfaces of Mars and Jupiter, where S is in meters and T is in seconds. So it says on Mars, S equals 1.86 T squared, and Jupiter, S equals 11.44 T squared. How long would it take overall? Okay, we'll get to that. So first thing you gotta do is just understand what you were given. What do those mean? It tells us S is in meters and T is in seconds, and this is equations for free fall. So this just means, you know, if you have something, if you drop something on Mars, T is the number of seconds that it falls, and S is the distance off the ground. So if you drop something and it falls for 10 seconds, plug in 10 for T, that'd be 100 times 1.86. It would fall like 186 feet, or I don't remember what it was. S was in meters. So it would fall 186 meters. So that's what those equations are. And it says, how long would it take a rock falling from rest to reach a velocity of 16.6 meters per second on each planet? So the question is asking for how long it would take a rock falling to reach that velocity. Well, I've told you, when you do derivatives, when you do derivatives, derivative is like, we've talked about, it's like the slope of a graph. And when you're looking at, and slope, I was going to say when you're looking at functions, but slope is just the rate of change. It's how something changes over time. Like slope is rise over run. It's how the values change, right? That's all slope is. So derivatives are just rate of change. It's the rate at which things change. I can't say that enough times. So if you do the derivative of this, so you do, that's just, you can do the derivative of that with respect to time. You know how to do power rule. So that would be what? 2 times 1.86. What does that give you? 3.72 T. So the derivative of position is velocity, because that's the way the position is changing. That's the rate that the velocity, the rate the position changes, right? So the rate the position changes, that'd be like saying, this is position, this is meters, and this is seconds, or what is it? Was T seconds? Yeah. I don't know. And I had some graph. Who cares what it looks like? Well, I guess that's a parabola-looking thing. The slope would be meters per second. And meters per second, those units give you velocity. Does that make sense? Right? Meters per second, the rate of change, the way the change in meters for every how many seconds, whatever. So there's your derivative of that. That's your velocity equation. So if you plug in numbers for t here, like earlier we plugged in 10 for t, and we got 186 meters, that means if it fell for 10 seconds, it would fall 186 meters. If you plug in 10 for t on this one, you would get 10 times 3.72. That would give you 37.2 meters per second. That means after 10 seconds, it would be traveling this fast. Right? So the question asks, well, the question, how long would it take to get to 16.6 meters per second? Well, this is pretty easy now. We want it to be going this fast, so if we just say 16.6 meters per second equals 3.72 t, we could solve for t to give us the time it would take to get to that speed. And that's where you just divide it by 3.72. And got, I don't remember what the answer was, 4.46 seconds. Same thing over here. You're given a position function. Do the derivative of that to get your velocity equation. So if you just do the derivative of that, you get 22.88 t, right? And you can just write velocity. That's how you know, that's what your velocity would equal. You want it to be that, so you just plug in 16.6 for velocity. Oops, sorry. And that's, I already gave you the answer, so who cares? Solve for t, and that's how you get your answer. 18 was one of the particle problems, right? Or was it 18? Yeah, it was oh no, this is, oh, it's a rock. What? Am I looking at the right? Yeah. I thought 18 was a particle problem. Which one am I thinking of? Oh, 20 is the one, the particle one. 18 is launching a rocket. Okay. We'll do this one first. So 18 launching a rocket, motor rocket, launch. I was thinking of 20. Okay, yeah, it's a graph of velocity, okay, versus time for a rocket. So now you have to understand what you're given here. You're not given position in this case, you're given velocity. Okay, so answer the questions. A, how fast was the rocket climbing when the engine stopped? So in this you just have to kind of think, well, when the engine stops, what's going to happen? Here you look, you got the rocket launch, the velocity is increasing, 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 increasing. The velocity stops increasing, and then it starts decreasing. But it's still positive. So this, just because this line's starting to move down, that doesn't mean the rocket is starting to move down. Remember, this is velocity, this is not position. So it starts out at 0 feet per second, and it goes really fast, and it hits its fastest point, but now it's slowing down. It's still traveling upward, right? The velocity is still positive. It's still traveling upward, but just not as fast as it was before. Right here, velocity hits 0. That's like the peak of the rocket. It's going to stop. And then right here is actually where it starts turning around and coming back down to Earth. That's when the velocity goes negative, because once the velocity is negative, now it's traveling back down towards the Earth. And then right here, all of a sudden, the velocity becomes less and less negative. So what do you think happens right there? So velocity is becoming more and more negative. It's traveling back down to Earth faster and faster and faster and faster. All of a sudden, it's still going back down to Earth. It's not changing direction. It's still falling back down to Earth, but not as fast as it was before. So that's where the parachute popped out. So now it's still falling. The velocity is still negative, but it's just not falling as fast as it was before. So that's how you have to really pay attention to what you're given and think about it, because I think you guys are just used to thinking of it as position. So how fast was the rocket climbing when the engine stopped? We can answer that question now. So it's going faster and faster and faster and faster. All of a sudden it stops. It reaches its fastest speed right here. And then it's still traveling upward, but not as fast as it was before. So that's where the engine's going to stop right there. Because you got to think about it, when the engine's burning, it's going faster and faster and faster. As soon as the engine stops burning, gravity's acting on it, so it's going to start slowing down. It's still going up, but it's just going to start slowing down because gravity's forcing on it. So right there, that's how fast was it going? I don't know. Estimate. I think I said like 190 in my answer. How many seconds did the engine burn? Well, right there, we know that's when the engine stopped burning. So what's that, like 2 seconds, 2.1 seconds? Whatever, right there. When did the rocket reach its highest point? A lot of people would say, oh, 2 seconds, because that's where the graph said at highest. But no, you have to think. It's traveling upward this whole region right here until right there. When the velocity hits 0 again, so it's going up and up and up. When the velocity hits 0, it's kind of at its peak before it starts falling back down. Right here, when the velocity goes negative. So the highest point that it reaches is going to be at 8 seconds, because you have all this positive velocity going up, and right there is when it's going to stop at its highest point. And then what was the velocity then? Obviously 0, because that's when it turns around and falls back down. Let's see here. When did the parachute pop out? I think we already answered that question. Down here we have a negative velocity, which negative velocity just means it's falling back towards the Earth. And it's getting more and more negative, so it's falling faster and faster and faster and faster. And all of a sudden right here, boom, it's still negative. It's like right here at whatever that is, like 11 seconds. Your velocity's still negative, so it's still falling back to Earth. But it's just not as negative as it was down here. So it's still falling, but it's falling slower and slower and slower. So that's how you can tell that that's where the parachute popped out. How fast was it falling then? You just read like what, -90? Or you could say the velocity was -90 feet per second, or you could say it was falling at 90 feet per second. And then, how long did the rocket fall before the parachute opened? That one's kind of tricky. You might be like, oh, 11 seconds or 10 point whatever. No, it says how long did the rocket fall. So remember, it was only falling. This whole time it's positive velocity, so it's traveling upward. It's still traveling upward all the way clear to here. Right there it reaches its highest point. So this is where it starts falling when velocity is negative. So it only falls for 2 point whatever seconds. I think I said 2.8 seconds, whatever. Almost 3 seconds before the parachute opens. And then, when was the acceleration the greatest? So that's what you have to know, that what acceleration is. I've told you acceleration is the derivative of velocity. Well, what does that mean? Remember, derivatives are just rates of change. So acceleration is how the velocity is changing, right? If you're accelerating, your velocity is increasing, right? That's what that means. Like if you're in your car and you're driving 70 miles an hour just with the cruise control on, you're not accelerating. But if you start to accelerate, your velocity is going to change. It's going to start increasing. So acceleration is the rate of change of your velocity, or the derivative. Well, if we're looking at a graph, derivatives, we know, we look at those with slopes. So it's basically asking, if we're asking when is the acceleration greatest, you got to think, when is the slope of this line the greatest, if you're looking at a graph. If we had functions, you could just do the derivative, right? Do your power rule, and you can do it that way. But since we have a graph here, we don't have a function, we're just going to look at slopes. So when is the acceleration the greatest? Well, all through right here, it should be obvious the acceleration's negative, because that's a negative slope, and it's pretty constant. It's a line. Here we've got positive acceleration, and here we've got positive acceleration. Right, this is positive acceleration because the engine's burning. It's moving upward, and it's going upward faster and faster and faster, so it's accelerating. The velocity's increasing, so it's accelerating positively. Here, this is also acceleration because the velocity is becoming less negative. And that's kind of confusing, and I've made a little video to help explain this idea, and it's going to play right after I explain this problem. But So greatest acceleration, like I said, just greatest slope of this whole thing. And you just got to kind of estimate on this. That's pretty steep right there. Just kind of do rise over run and just kind of pick like 2 points. Let's see, like if I do this one, I got a rise of, I don't know, what are these going by? 10s, 50, 60, 70, 80, 90. Yeah, these are like 10s. It's like this would be like up 10, 20 over, what are these going by? 0.2s, I think. This would be like up 20 over 0.2, so it's 20 over 0.2. 100. And this is like, well, this is way more. This is, yeah, this only goes like, yeah, this goes up a whole bunch over, not as much. So obviously, the slope right there, that slope is much steeper than that slope. So your greatest acceleration is going to be right before the engine stopped burning. Like right there, right at 2 seconds probably. Or right before 2 seconds. When was the acceleration constant? Well, that's this whole time when it was falling. If you know anything about physics, you know the force of gravity is constant. So the acceleration is constant the whole time it was falling back to Earth, or the slope was constant. These are curves, so the slope is constantly changing. This is a nice straight line, so the derivative of that is just, it's constantly the same. So now, I've done a little demonstration before we talk about this particle problem about velocity and acceleration. So here's that. Okay. I'm going to try to give you a visual for your velocity and acceleration problems. So my wife will be the particle in those particle problems. And she's going to have velocity. I'm going to be acceleration. So you have something that's moving at a positive velocity. And it's a negative acceleration. It'll eventually slow her down and then start going the other way faster and faster and faster and faster. That's what acceleration does. It changes the velocity. If she has a positive velocity and I'm positive acceleration, I'm just going to make her go faster and faster and faster. We have a guest star in the film. Don't push her. Okay? Same thing goes. If she's got negative velocity, go a bit further.
What?
Go further. If she's got negative velocity and I'm positive acceleration, she'll be coming this way. As soon as the acceleration starts to force, you'll slow her down, and then eventually turn around and go faster and faster and faster and faster. Same thing if she's got negative velocity and there's negative acceleration, it's just going to make her speed up in the negative direction. That's how velocity, the acceleration changes the velocity. Talk more about that when I'm not in the hallway here. Okay. I don't know if that'll help with this particular problem, but it helps with some of these problems. So usually I would do that in front of the class, but obviously I'm not there, so that can't happen. So this problem on 20, it's just a particle moving along the line. And we have position. Oh, so they're giving us a position, S of t, right there. S is in meters, t is in seconds again. And they want the instantaneous velocity at any time t. Remember, velocity is just the rate of change of the position. Well, rate of change is its derivative. So it's just the derivative of our position. If we had a graph, we would just find the slope. But since they give us the function, if they want the velocity function, right? Instantaneous velocity at any time t. That's just the derivative of this. So A, you just have to do the derivative of this. It's just v of t. Do your power rule. That's it. That's going to be your velocity at whatever time t. So you plug in, if it's like, what's the velocity at 5 seconds? You plug in 5 for t. That's it. If it's how far, or what's the position at 5 seconds, you plug in 5 for t on that thing. So you use these equations to find positions and velocities if you need to. B, find the acceleration of the particle at any time t. Well, acceleration is just the change of the velocity. So the rate of change of the velocity. So you just do the derivative again. I'm starting to realize my little video isn't going to really help with this problem, probably. So there's that. That's it, the derivative of that one. See, oh, here we go. When is the particle at rest? I gotta think. Oh no, that's the wrong problem. Oh no, same question. When is the particle at rest? See, at rest means what? It means you're not moving, right? And when you're not moving, which of these explain motion? That doesn't. That tells you where you're at. That doesn't. That tells you how fast your speed is changing. But velocity tells you how fast you're moving. So if you're at rest, your velocity is 0. So all you have to do, if you want to know if something's at rest, you plug in 0 for your velocity equation. Oh, no. Stupid. You don't plug in 0. That would be time is equal to 0. That would be the velocity at 0 seconds. I want to know when the velocity is 0, meaning I want to solve for t when velocity is 0. So I'm going to go. Right. If you're trying to figure out when something happens, you're going to solve for t. So you plug in 0 for the velocity, solve for time. So you can probably factor that. Looks like we have to do quadratic formula. Or look at, hey, it's a calculator problem. So remember, you can graph it and do calc zeros. You can do that. Good little review for how to use your calculator. I think I did quadratic formula on my answers, but if it's a calculator problem, you might as well use your tools. Just graph it. Plus this is way faster. Alright, since it's setting it equal to 0, we're just solving when this thing equals 0. So right there and right there. Remember calc right there. 0, hit enter. Got to move the little cursor to the left. Whoops. Calc 0. See, this tells you where your cursor's at. So I know I want to be like at 1. There's my little cursor there. So I'm to the left of it, hit enter. Go to the right of it, hit enter. Guess. Looks like about right there, hit enter. 1.45 seconds. So t will be 1.45. Do the same thing for the other one. Calc 0, go to the left of it, hit enter. Oops. Or I could just type in a number, I think. Go to the right of it, hit enter. Guess. There it is, 3.22. Alright, those are the times that'll make the velocity 0. So that's how you know when the particle is at rest. And then D, describe the motion of the particle. At what values of t does the particle change direction? Well, when it says describe the motion, it's just saying how is it moving. You could, right here we've got our velocity graph, right? So it looks like it's going to start out with a negative velocity. When time is 0, our velocity is negative. So that means it's going to start out moving to the left, right? But negative velocity is this way, if you're thinking position, right? This is a particle on a number line. Here's my number line. I don't know where well, I could figure it out. If I use my position function, when time is 0, so right when this thing starts, that's 0, 0, 0, 8. So this particle is going to start way over here at 8. It's going to start right there. And looking at my velocity graph, I see that it's going to start with a negative velocity. And it's going to have a negative velocity until 1.45 seconds. So it's going to start at 8, and it's going to start moving to the left for 1.45 seconds. Then at that point, it's going to have it's going to have a positive velocity until 3.22 seconds. So it's going to move to the left for 1.45 seconds. Then it's going to turn around and move to the right for 3.22 seconds. And then it goes back to negative, so then it's going to start moving left again forever. How far does it move to the left? I don't know. I would have to use this. If I plugged in 1.45 for t here, I could figure out how far it moved to the left because it would give me a position. If I wanted to know where it was when it turned back So then it goes to the right. If I wanted to know where it turned back around to start moving to the left, I could plug that in for my position function. So some more of these types of questions are going to come up on the problems I'm going to give you today. Let's see, one more. I think I gave you 24. It says a body's velocity, so it gives you the velocity, find the speed each time the acceleration is 0. So it gives you velocity and it says find the speed whenever acceleration is 0. Well, if you want to work with acceleration being 0, that to me, that means, hey, if I just plug in 0 for acceleration and solve for time, that'll tell me when the acceleration is 0, right? So if I have my velocity equation, if I get my I got to get my acceleration equation. That's just the derivative of that, right? 6t squared minus 18t plus 12. So it says find the speed each time the acceleration is 0. Well, so now we're going to figure out when is the acceleration 0. At what time does that occur? So if I plug in 0 here, now you could factor that quadratic formula, use your calculator. It's a calculator problem. Probably use your calculator. But for the sake of time, we'll just go, I think the answers were t equals 2 and t equals 1. So however you did it, you get those for your time. That tells you that the acceleration at 1 second is 0 and the acceleration at 2 seconds is 0. So the question is, find the speed at those times. Well, so now you're just going to take these two times and plug them back into your velocity equation. So the v of 1 and v of 2. So you plug those in, and let's see, I think you get 0 if you plug that in, and if you plug in 2, you get -1, which that's not your answers, because it asks for speed, it didn't ask for velocity. Velocity has direction, right? If you're moving to the, this would mean if your velocity is -1 meters per second, it means you're moving to the left at 1 meter per second, but the speed of that is just 1 meter per second. Speed is just the absolute value of velocity. So your speeds would be 0 and 1. Whatever. So try some more of these. Probably call you guys tomorrow and see how it's going. Or they'll be watching this tomorrow, so that'd be Tuesday. Let's see, where'd my list go? That's probably good enough. Yeah, that's good enough. I had more, but I don't want to give you too many and have you be overwhelmed, because like I said, I have no idea how you're doing with it. So yeah, 13's more position velocity stuff. 22, same thing. Oh, 25. I want to talk about 25. I'm going to add one more. 36. It's really quick and easy. Do 36, too. 25 talks about draining a tank. So we talked a lot about position and velocity, but this one is, you got to understand what they're giving you. This one, it says the depth Y of fluid in a tank T hours after the valve is open. So you got a tank, Y is how deep the water is. T is how long it's been since there's a valve that they're going to open and the water's going to start draining, right? So you got a tank, you got water. This is Y, that's how deep it is. And then it's going to start draining. So after a certain time, it's going to drain down and down and down. So find the rate at which the water level is changing. So if you, hey, look at that, sounds like rate of change, right? Or it even tells you The rate of change is just the derivative of this. So you have to do the derivative of that thing, which sucks for you because you have to FOIL that out first so you can do your power rule. All right, t over 12 times t over 12 would be t squared over 144. Just a lot of algebra there. When is the fluid level in the tank falling fastest, slowest? How are you going to answer that? Good question. Maybe I don't know how much help I want to give you here. It's all about rates of change, though. So using your derivatives to answer these questions. So if y is the depth, dy dt would be, let's see, what are units here? Does it give us units? Oh, meters. And what's t? Hours. Right? So, and if you do the derivative of that, you're looking at meters per hour. It's how many meters per hour the water level is falling. So when is it falling the fastest? Key question is when, so you know you're solving for t. Keep in mind it's a calculator problem. Maybe you want to graph it, see when it's the highest and lowest, right? Slowest would be when it's the lowest point. I'm not going to tell you which one to graph, whether you want to graph position, or I was almost going to say position of velocity, whether you want to graph depth or you want to graph the change in depth over time. That's going to work together as a class on that one. That'll be fun. Let's see, what else did I say? 26 says use blah blah blah, but maybe I should just, let's just take that one off. Don't do 26. Let's do 13, 22, 25, 36. So you can do those four, I'd be happy. Okay, bye.